Hello, my name is Harry Wilcox from the Semper Group, and today we're going to be running through the brief and more basic features on the Opticline. So I'm stood next to a C9104, so that signifies that the system is 900mm tall and 140mm in diameter capacity. There are different sizes and specifications of the systems. So we have a CS variant, which is our lesser accurate system, more the entry-level units, and they range from a 155, which is 150mm in length by 50mm in diameter capacity, all the way up to 900 by 140. Now, the system that I'm stood next to is the higher accuracy system. So this is our C variant, and they go from a 203, which is 200 by 30, all the way up to 1.2 meters by 230 diameter as a standard. So we're going to start by looking at diameters and lengths. So I've got one of our demonstration components here that I'm going to place into the machine. And by starting a new program, what we're going to do is create a contour for the part. So by going to our create new program from the machine, if I click next, what the system's going to do is it's going to scan the contour of the component. And from here we can start to decipher the features that we want to measure. So obviously in this section we're looking at the diameters and lengths. So you can see on the software that the full 900mm has been scanned. So what we're going to do is we're just going to select the area where our component is. So you can see our work holdings either side. So we've got a center and a ball on the top. And from here now we're in the position where we can create our length reference and our rotational reference. So I'm going to use the bottom of the component as my length reference, and then I'm going to use a valley feature. So the valley feature is effectively looking for a roundness plot and trying to find a cutout or a slot within that plot, and it takes the center of that position. So from here I can click finish, give my program a name, and click save my test plan. So from here we can go to the live mode on the Opticline, and what we're able to do now is when we program the system, we're actually creating the features and the system will go and measure them straight away. So as a starting point, obviously the component I'm making the assumption is straight on the fixture. What I am going to do is to just tidy that up by creating an axis. So we could measure the diameter straight off without doing that, but we could see if the part had been manufactured incorrectly that we would inherit some error into the measurements. So I'm taking a roundness plot at either side of the component, and from here I'm going to use the axis tool. I would like a rotational axis, and I'm going to select the two roundness plots that we've taken. So now I have axis 01, and from here we can relate our diameters and lengths to this axis. Okay? So to measure a diameter, we can go to our dimensions, diameter general, and I can select an area where I would like the diameter to be taken. And because we are in our live mode, straight away the diameter is measured. If we go to our detailed contour, you can see the surface. And if I was to go to our core section value, which is our effectively the magnification, you can now see that we're picking up the turning marks of the component. Okay, so it's a really nice method for measuring this diameter. On the right hand side, we have different methods to be able to measure the diameter. So we could interpolate, so we can measure multiple positions around the diameter. We can relate it to our reference axis, so that slot that we found at the start. And when we look at the evaluation extended, we can also relate it to our axis. Okay? The evaluation method here, we can change to be looking for the minimum, maximum or mean values. So if I was to go to the maximum, we're now looking at the top of the peaks as opposed to the mean of it's effectively a least squared fit on this side. Okay. So there's another way to measure a diameter is to use our roundness plot. So sometimes if we're trying to fit an external diameter into a bore, what we would want to do is we want to make sure that the shape of that diameter is okay as well as the size. Okay? So by measuring a roundness, we're then able to apply some filtering. So these are minimum circumscribed, minimum inscribed kind of features. And I can relate a diameter to that roundness. So if I go to my diameter rotational reference, I can select the roundness that I've just measured. And now when we look at our detailed plot, you can see that we've got the diameter as outputted from our roundness. So if we were trying to understand whether the part had any shape to it, we could use this to see whether it's tri-lobed, lobed, all of those kind of features. Because sometimes it's really important if a component's fitting into another part that the diameter and the roundness is correct. Okay. So that's a brief overview on the diameter side of things and how we can program the system to do that. So now what we're going to look at is a length position, okay? So by going to our references, I can go to my length position general, and if I was to select the edge on the top of the part, so you can see when we click to measure the length position, what we're finding is that this blue line is where we're intersecting. So I'll always try and bring this as close to the edge as I can, just as a sort of a best practice. So if I was to duplicate this feature and measure another length position, so I'm going to drag this feature down the component to this edge here, and again I'm going to bring our intersection across. So you can see now where we're measuring our length, you can see the fit of the edge. We have very similar principles with the features where we can control the rotation, so we can control where the position of that's taken. We can relate it to our axis again, and we can also look for maximum or minimum edges along this edge, okay? So to output our dimension for this case, what I'm going to do is go to my length position, so a distance. I'm going to select PO1, PO2, and from here you can see that we're calculating the distance between these features. So the only other thing I would need to do now from an operator's perspective is to just type in my nominal value and our tolerance band, okay? So there's lots of other ways that we can measure length positions. There's intersections, there's sort of core references, diameter references, all of these kind of ways that we can do our diameters and our length positions as well. We've got all sorts of different calculations, looking at the center point of radiuses, positions along a cone. So there's lots of methods that we can use to measure all of the types of parts that our clients have, okay? So that's a very brief overview on the methods we can use to measure the diameter and length positions. So we're going to move on to our next section now. So now we're going to take a look at radius and chamfer features. So on the component there's lots of chamfers, angles and radii, so we're just going to take a look at some of the more challenging ones to measure and show you the basic principles on how we can do that. So going to the software, I've got the program set up with our previous roundness plots and the axis, and then I've got my length position, which is our LREF down on this left hand corner. So what we're going to do is we're going to start by measuring this chamfer here. So I can go to my search tool and I can type in angle, and you can see that I get the angle general pop up. So if I select this feature, I can decipher the area that I would like to measure the chamfer. Now, a key thing that we need to make sure that we do when we're measuring a smaller feature is to refer it to another sort of position or diameter. So what I'm going to do here is I'm going to use my LREF, which is obviously our datum setup, to define the boundary in where I measure this part. And the reason this is really important is that if we weren't to use a reference, if this LREF was to move, what we could see happen is that we start to take in some of the flat here, the radius on the corner, and also in the other direction we might end up measuring the radius as opposed to the angle. So what we do is we'll always define the reference position, and from there we should be able to control the position of where that chamfer is. So if we go to our detailed contour now, you can see we've got a few little defects and dents on this part, but we're getting a really nice depiction of that surface. If we zoom all the way in, you can start to see the turning marks on this chamfer. So that's the manufacturing process for this component, but it really sort of shows the resolution of the system. We're working to about 0.1 of a micron on the C-series Opticlines. Okay, so it's a very quick overview on the chamfers, and now we're going to look at the radius features. So for larger radiuses, so this feature here, we can see the cursor is, I can just use a standard setup. So I'm going to look for radius, and you can see we have the radius setup. I can go to radius general. If I select that feature, I can drag a boundary similar to we did before, and you can see within our detailed contour we get a really nice fit for the size. Okay. Now the more challenging radii that our customers want to measure are undercut features like this. Okay. So other optical systems can sometimes struggle with these, one from the resolution side of things and the ways that they can manipulate the data to hold the part in the correct orientation. So having the capability for the axis and also the resolution of the optics is a really good sort of ticking point to be able to measure these features. Okay. So if I go back to our search tool, I'm going to start by measuring a diameter, and the importance of this will come sort of true in a second when we come to measure the feature. So now I've got my diameter measured in that undercut. What I'm going to do is I'm going to duplicate my radius feature. So one of the tools within the software is we can duplicate features. It makes it much easier, so I don't have to keep going to my left-hand toolbar. And if I just sort of bring down the area we're looking to measure, we can start to get our measurement strategy created. So now on the parameters for my radius, I can go to the measuring range, which is for the camera here, and we've got limited diameter. And if I'm to toggle this to one measured value, what I can now do is I can use my diameter as a reference feature to measure this edge, okay? So I'm going to bring an offset of our measured value of 0.01. I'm just going to bring that up a little bit more, just so we're off of this edge. And then I'm going to drop this down to 0.15, okay? And I'm just going to increase this now. So the benefit of being able to do this is when the part edge was to move, so if this edge was to slide where my cursor is, left and right, we're going to make sure that we're always measuring the radius correctly, okay? So we've created this boundary, so as this edge moves, we're not going to be caught out by measuring a sort of false positive. So if I go to our detailed contour now, when we zoom all the way into this very small feature, again, it's sort of amplifying the turning marks because we're looking at a much smaller feature now. When we look at the results detail, we're looking at a 0.35 rad in this corner, okay? So we can now go and look at the other side. And you can see again, we're getting a really nice fit for this radius feature, okay? So it sort of really shows the capability of the system when you're looking at the smaller features as well as the larger features that you also need to have that accuracy on, okay? So that was a very quick overview on the different methods we can use for measuring a radii and a chamfer. Now we're going to take a look at a couple of the form features that you can do on the Opticline. We're not going to go over all of them, but these are the more basic functions that people tend to use, okay? So going to the software, the most prominent that we use with our clients is the roundness function. So if we go to our form deviation, we can look at the roundness. So there's lots of different ways that we can measure roundness, but we're going to just look at the general feature to start with, okay? So if I go to one of our grooves, I'm going to take our roundness plot here. Now, the evaluation mode to the roundness is the critical bit within these systems. It's how you can change the resolution, the evaluation mode, the filtering, and fundamentally what we're trying to find on that roundness as well. So here we've got our least squared fit, and we're using a UPR filtering of 0 to 15. So some of our clients have specifications that we need to basis this on a 0 to 50, and we can then, or we can do a freely defined one, so we select the amount of filtering that we apply, okay? When we're looking at actually the calculation, so we've got our minimum inscribed, minimum circumscribed, so what I can do is select the differences to these to show the differences on our contour. So if I just go to our core section view, you can see the fit that we're finding on here. It's a little bit of dirt on the part. And if I'm just going to move that away from the dirt, and then we'll select our MCCI, and we go to here, you can see that we're getting a different fit for the component. So this could actually be a bit of a defect on the part as opposed to being a piece of dirt. So you can see the machining process, it looks like it's bringing in a slight bit of mismatch here. So this could be where the tool is sort of touching the component, creating the feature, and then as it comes off, we're obviously getting this step that you can see, okay? So that's a really basic overview of roundness. What we're going to look at next is like profile forms. So if we go to our form deviation tool, we've got our profile form general and our tolerance profiles. So these are quite often used for looking at sort of an overall depiction of a surface. We tend to find that customers will specify a position from X to Z, and what we need to do is to measure the profile in that area, okay? So I'll run through both of these principles. So first of all, we'll go to our profile form general. I've selected this edge here. I've already loaded in our profile for this. So that's why I'm taking that area. If I go to axis 01, I select that. And then what we need to do is as we drop down here, you can see that we've got a drop down for our form features demo. And I'll show you in a second how we load those in, okay? So if I go to this selection here, go to our detailed contour, what I want to look at is the form deviation. So as we zoom in here, you can see the deviation of the form. These are some little pieces of debris that we've picked up. I haven't cleaned the component, but effectively that's what we can see along the part here. So if we now want to look at a tolerance profile, what I can do is once again go to our form deviation. We can go to our tolerance profile. I'm going to use the same selected area, refer it to our axis, and this time I have 1, which is the form features demo 1. And now when we look at the profile, we zoom in, we can see the deviation that we'd be looking for to check whether the part is visually within spec, okay? So what quite a lot of our clients do is within our parameters, they will rotate the component. So what we'll do is we would go to a interpreted measurement, and we can then rotate the component on a specific number of times to measure this form deviation in, say, 10, 15 positions, to sort of reenact what a surface profile call out is doing. Okay, so that's helping us to understand what's happening across the whole surface as opposed to the individual. So those are just a couple of the small form features that we can do. There's lots more, so if there's any questions on those, please don't hesitate to ask in the chat. But yes, a little overview on how we can program them as well. So now we're taking a look at the optimization techniques that we can use within the software. So the Opticline system, as opposed to some of our competitors within this field, will use multiple objectives. So the idea behind that is that we can keep the resolution as we go to larger diameters. So this 1.4 system here, effectively we have a 50mm camera, we have another one above it, and then another one to the side of that. And what that does is that creates an overlap so that we get our 140mm diameter, but we maintain resolution from a 1mm measurement all the way up to 140mm. Okay, so what I've done is I've created a program. I've just added a few features in to demonstrate the principles of how this would run. And what we've got in the bottom right corner on the software is our runtime. So I've added in features like the form that we were talking about previously in multiple positions now. So we're measuring that in 5 positions. We've got more diameters. We can see the turning marks really clearly on that surface. And then we've got some other features like cylindricity. So we're picking up the form of the surface. You can see this has been manufactured as slightly lobed. So it's quite a nice call out there. And to measure all of these features, that took 46 seconds. So on the software, we have this optimization button here. So what I can do is I can click optimize and click OK. And what the software does is it's trying to select the best camera to use for the measurement. So obviously where we have the 3 cameras, we're selecting the best one to use for the measurement to reduce the time that it's going to take to measure. Okay, so it's the methodology for us to be able to speed up programs. If we have a component in a part family that's only up to a 40mm diameter, I can exclude the other 2 objectives, but that part family might go to 130, 135mm diameter, so I need to have the capability of the larger diameters on the system. Okay, so now what it's doing is it's running through its optimized path, and in a second it will give us a runtime to be able to measure this feature. Okay, so it was 46.5 seconds before, so now if I click accept and run, we should see an improvement to the measurement time. Okay, so there isn't a defined percentage increase because it depends on the features and the number of features being used by each camera. But it always brings some form of improvement, we tend to find. So we're just letting the measurement complete. So you can see we've gone from a 45.4, I think it was, to 26.7. So it's almost a 50% reduction in the inspection time. Okay. So that's a very quick overview on the optimization. One other button that I wanted to show you within the system is if we go to create a new program, so starting from fresh. So when we load our new test plan, we can load this in from a contour. So if you had a DXF file or a TXT file, we can load the contour of that in. In this case, I don't have one for the component, so I'm going to go off of the machine. Now the benefit to loading in your DXF is that you'll have the nominal data associated to that component already within the DXF. So I know that the component is the exact size. So there's a button that we can use after I've created the sort of start of my program. So if I draw this selection here, I'm going to use the same features we did previously. Go to my value tool, and go to finish, add in a name. So we'll call it form feature demo. So if I go to my test plan here, I can go to create test characteristics. And what this brings up is a window that pops up to say, would I like distance, diameters and cones? And am I measuring a ground or a turn surface? So I'm measuring a turn surface. So if I click OK here, so what the software has done is it's tried to find every feature automatically on this contour that you see. So you can imagine when I select into the individual diameters that they're picking up a slightly different nominal value. That's because the component isn't manufactured to spec, so the nominal defined is effectively the measured value. So if we had a DXF loaded in that was correct, the nominal value would be correct, and then from here I can click start, and I've already created a program to measure all of those diameters and those length positions. Okay, so as a starting point to build a program, it's quite a useful tool to use. So you can see we've probably measured maybe 20 characteristics there, and from the off of me starting a program to finished, it's taken 15.5 seconds. Okay, so it's quite a nice tool within the software that we've got. So that's a very quick overview on how we can optimize programs and some of the tools that we can use to speed up the programming as well. So our last section, we're going to take a look at how we can export the measurement data to different softwares and different formats. So on the software, if we go straight to it, on our test plan header folder, so this one here where my mouse is, we've got our export options. Okay, so sort of working our way along these, relatively self-explanatory. There's a automated QDAS function, so if we were to turn the QDAS function on, we can then create a template to export our features to QDAS. This would be for this program, so if you wanted to set a default export, what we can do is export the specific default functions, then across say 5, 10, 30 programs, we're using the same export settings across the board. Okay, if you wanted a specific one, what you could do is use specific for this test, and then we can go in and create those test parameters again. Okay, all right. So it's just a little overview on the principle of what we can do within the QDAS export. This is becoming a much sort of well-used software within the industry, so we're starting to see a lot more of our clients ask questions about using QDAS, so it's good to know that we've got the capability to do it. So the standard exports that we tend to find, the CSV, mini CSV. The mini CSV is effectively just a sort of stripped back version of our CSV. If we go into our settings for these, the same principle again, it's a very similar window. We can turn this on by either clicking here or by clicking the actual icon itself. What that's going to do is that's going to use the currently the basic settings. If we go into here, we can specify how we would like the settings to be done, as well as the characteristics that come across, the features, the separations, all of that kind of thing, so that we're creating that template for you to be able to use across the board for all of your components. The PDF function, so the PDF function is effectively us. So if I was to turn this on, if we go to our print and we look at our export, so currently this is sort of the base standard export that we use. If we go to the edit tool, what we're able to do is to be able to create specific PDF formats for you. So if you needed specific identifiers within the program, you needed to know part temperature, that kind of thing, what we can do within this setup here is there's lots of different functions to create the template that you need for your PDF export to either send to your customers or your internal customers that you might have. Okay. So going back to our test plan header, the last one to touch on is the measurement data. Okay, so this is a relatively new export function for us at Sempra. And what we're able to do with this tool is to be able to export to controllers, machine tools, or other processes within the setup that you might have. So an example of a client that we're working with currently that's got multiple Opticlines within their facility. What they're doing is they're feeding data from the Opticline to 6 different machine tools. They're sort of lathe systems, and the idea behind that is that the one Opticline is controlling the process for the 6 tools that they're using. So different parts are coming in from different machines. What we're doing is we're exporting the results and the offsets to the machine directly, so it's effectively a closed loop operation. So what they're going to have is they're going to have a gripper in between loading the parts from the machines, so we're helping them to create a closed loop manufacturing and measurement cell. Okay, so this is quite an important one. It's very beneficial to a lot of our clients now. We're starting to see a massive uptake in the use of these scripts to create those specific outputs for the different controller types. Okay, so it's a bit of an overview just on the types of softwares we can export to and the ways in which you set up those databases. Okay, thanks ever so much for your time, and speak to you shortly.